All right. Hope you guys are doing well today. We have what I feel is a very interesting topic to talk about today, and that is the operational amplifier. So before we talk about how to analyze op-amp circuits and what they do, I want to introduce you guys to something, and it is going to be incredibly intimidating. Okay. So I'm going to drop a picture in here. And let me make it smaller so we can all see it at the same time. So this is what the internal circuitry of an op amp might look like. And this is actually a very simplified version, which probably is very scary to you guys. So this particular circuit um, is the functional, essentially block diagram of a mu A741 general purpose op amp that's used in a lot of simple analog signal processing systems like music players, guitar effects pedals, things like that. Okay. This particular circuit, as it's drawn here, contains 22 bipolar junction transistors, 11 resistors, one diode, and one capacitor. So we have a very good understanding of what resistors do. We have a reasonable understanding of what capacitors do. We haven't really talked about diodes in this class, and for what it's worth, we're not going to. And we also haven't talked about transistors in this class. And your only experience with transistors before was in the Engineering 120 series when you were effectively just using them as an electronic switch. In this particular circuit, they're being used as amplifiers, which is just a whole different bag of cats. So we have this terrifying looking thing here. And somehow we are going to analyze circuits that contain operational amplifiers. Well, before we get into that and the much simplified models and the rules that we're going to deal with, I want to make a couple of quick observations about the operational amplifier as a whole. Okay. So the first thing that I want us to kind of notice here is these two pins effectively called N minus and N plus. Okay. So an operational amplifier is a device that has a differential input, meaning that you can apply multiple input signals to it. And really, at its most fundamental level, what it's doing is amplifying the difference in those two voltages. That functionality is almost never actually used, but that's kind of going on in the background. Okay. So we're going to expect to have multiple input signals for circuits containing op amps. Um, we've got this guy up here labeled VCC plus, and this guy down here labeled VCC minus. So these are our power pins, okay? So an operational amplifier is an example of an active device, meaning that it only behaves the way that we want it to if we supply it with external power. So resistors exhibit resistance regardless of whether they're connected to a circuit or not. Similarly, inductors exhibit inductance, capacitors exhibit capacitances. Op amps only behave as amplifiers if they are powered. If they're not powered, they don't really do much of anything. Okay. Over here on the right-hand side, we have this output pin. So this means that we have a single output signal out of our amplifier. So we effectively put some signals in, we amplify them in some way, shape, or form that we'll talk about later. And then we get a single output signal measured with respect to ground. Okay. And then lastly over here, these are the ones that are least important to us. This is our offset null 1 and offset null 2 pins. Not all op amps actually have these pins, but they are there to correct for small manufacturing errors that occur within CMOS fabrication processes. So op amps are examples of integrated circuits where everything is integrated monolithically on a single silicon chip. And sometimes things get slightly askew when you're aligning the various fabrication masks and things like that. And what you might see is that if you put 0 volts on input plus and 0 volts on input minus, you might see a very small, on the order of a few millivolts, output signal because of those misalignment problems. Well, those offset null pins help you just negate that for high precision needs. Okay. So other than what we just talked about, we'll never deal with the offset pins again. Trevor just asked, what exactly is an op amp used for? The short answer for that is damn near everything. So in its most basic form, the operational amplifier is used to perform mathematical operations on signals. So we'll talk about some of those signal operations in class on Friday, but we can do things like adding signals, subtracting signals, integrating signals, differentiating signals. With multiple op amps, we can multiply signals, we can divide signals, we can do lots and lots of things. The operational amplifier is the brains of essentially all analog computing, which is actually coming back in style because analog computers can do some specific operations much, much faster than digital computers can. So op amps are literally everywhere. They are a fundamental building block of practically all electronics. So I guarantee you that if you've got a phone in your pocket, you've probably got at least 30 op amps in your pocket right now. They are ubiquitous in electronic systems. Um, okay, so let's get this big, scary, horrifying thing out of our mind, and let's talk about op amps from our perspective. Okay, so this symbol for an op amp is going to look something like this. We're going to have a triangle like so. And on the left-hand side are going to be our input terminals. So I'll put one of them here and another one of them here. And I'm going to put a minus sign on top and a plus sign on bottom, like so, so that it matches the functional block diagram representation that we looked at a moment ago. Okay. So the terminal that's attached to the minus sign is what's known as the inverting input terminal. And what we'll see after we work a few examples analyzing circuits that contain op amps is that, generally speaking, when a signal is applied at the inverting input, whatever the op amp is doing, it does that, but then it flips the polarity when we get to the output. So if we apply a positive polarity signal on the inverting input, we should expect to get a negative polarity signal at the output. Contrast that with the terminal that's attached to the plus sign. This is the non-inverting input. And so any input signal that we apply at the non-inverting input terminal maintains its polarity when it hits the output. So if we apply a positive signal at the non-inverting input, we get a positive signal at the output. Over here on the right, I will now actually draw our output terminal. And the output of an operational amplifier is always going to be a voltage. Okay. It will be a voltage measured with respect to ground. For what it's worth, our inverting input and non-inverting input signals are also usually voltages measured with respect to ground. They don't have to be, but the output signal is always a voltage measured with respect to ground. Like I said a moment ago, when we put something on the inverting input, a positive signal is going to turn negative at the output. If we put it at the non-inverting input, a positive signal is going to stay positive at the output. A couple of other pins that we're going to represent on here. I'll do the power ones in blue. So here is our VCC plus pin where we supply positive power. And here is our VCC minus pin where we supply negative power. So we might see like plus and minus 9 volts applied to our VCC plus and minus pins. Some op amps might require plus and minus 18 volts. There are some op amps that are designed for single supplies, which means VCC minus is always just tied to ground or zero. Not particularly important. And these power supply pins are not going to have any impact whatsoever on the analysis that we do. We just kind of need to have in the back of our mind that op amps require power in order to operate. And then lastly, in pink here, I'm going to draw the offset null pins. So let's just call this offset plus and offset minus. And like I said, we're really not going to mess with these at all in this class. So if we look at this schematic representation, we can see that an operational amplifier is a 7-terminal device. So that's very, very different than anything else that we've dealt with in this class. Resistors, capacitors, inductors, current sources, voltage sources, they've all been 2-terminal devices. The diodes that you dealt with in the Engineering 120 series were 2-terminal devices. The transistors that you dealt with were 3-terminal devices. Relays were 4-terminal devices, but this guy's got 7, okay? So it can be rather intimidating, but from a circuit analysis perspective, only the input terminals and the output terminals really do anything for us, okay? Before we move on to the rules for using an op amp and all that kind of good stuff, I want to talk to you about the packaging just really quickly. For those of you that are going into electrical engineering, mechanical engineering, biomedical engineering, and a few of you that are going into chemical engineering will actually deal with physical op amp circuits fairly regularly because they are how we take the output of sensors like pressure sensors or a sensor that's measuring brain activity or something like that, and then amplify it in order to have some larger measurable signal that we can do things with. Okay. So an op amp package nowadays typically looks something like this. So you'll have this kind of plastic enclosure type thing, like so. And then there are going to be 8 legs sticking off of it that you could plug into a breadboard. Or if you were so inclined, solder to and all of that kind of good stuff as well. Okay. So I said an op amp is a 7-terminal device, and this package has 8 legs, which means one of them is literally not connected to anything. Okay. It just doesn't make sense to have a 7-pin chip because that's not the way that circuit boards and breadboards and things like that are laid out. Okay. Usually, you will see on one side of the package either an indentation like this that's kind of a semicircle, or you might see a small circular indentation like so. This is what's telling you where pin 1 is located on the actual chip. So pin 1 is here, then we go 2, 3, 4, come over here, 5, 6, 7, and 8, like so. And then depending on what company designed the op amps, the internal structure of the op amp, like you can't say pin 1 is always going to be the inverting input and pin 8 is always going to be the output. It depends on who made the op amp, all that kind of stuff is usually included on the data sheet for the actual device. Okay, so we've got our schematic diagram symbol. I've tried to describe what a physical op amp might look to you guys that are going to wind up using them later. Now let's talk about the op amp circuits that we're going to be analyzing in this class. So here in circuits 1, we are specifically only concerning ourselves with circuits that contain negative feedback. Okay. I'm not going to spend a whole hell of a lot of time talking about the benefits of negative feedback versus positive feedback versus open loop operation, because for the overwhelming majority of us, that part doesn't really matter. I would say 99% of op amp applications are actually in a negative feedback configuration. And so that's why that's the only thing that we're concerned about here in circuits 1. So I want to show you guys something just really quickly to as to how we can determine whether our circuit has negative feedback, positive feedback, or if it's an open loop system. Okay. So let's just call this bit right here feedback options. So on the left-hand side, I'm going to draw an op amp in an open loop configuration. Okay. So in an open loop configuration, we might have something like this. So here is our basic op amp with its terminals labeled. For the hell of it, I'm going to put the VCC plus and VCC minus terminals on here. And we might have some input signal, let's call it V1 of t applied at our inverting input, some input signal V2 of t applied at our non-inverting input, and our output would be over here on the right. So this is an example of an open loop configuration. Okay. So there is no feedback path that is connecting the output to either one of our input terminals. Okay. This is useful at times. This is how we set up what are called comparators for simply measuring signal strength with respect to some reference. So we could use a configuration like this in control systems if we want to set off an alarm if the temperature ever exceeds some specific set point. Okay, so nothing particularly difficult here. Think about it like what you were doing with your Arduinos, where you turned an LED on when a switch was closed or when you pressed a button or something like that. That's kind of what a comparator is doing, except that it doesn't require computing power to do that. It's doing it as an analog system. Okay. Then we might have a positive feedback system, which might look something like this. Okay. So starting with my basic op amp, and again, just adding in the supply voltages so that we remember it requires power. I'll stop doing this in a moment. We might do something like this, where we connect a resistor between the output terminal and the non-inverting input terminal. I'm going to label this resistor RF. So the subscript F just stands for feedback. So this is our feedback resistor. And then I might throw another resistor right here. I'm just going to call this guy R sub I. Maybe I ground this guy, and then I apply an input signal over here. Okay. So this circuit has positive feedback. And not that this is remotely important to practically any of you, but this particular circuit is what's called a Schmitt trigger. A Schmitt trigger circuit can be used for making analog to digital converters and things like that. It works very similar to how the comparators that I talked about a moment ago work, except that it also has what's called latching. So it kind of holds on to the signal until certain criteria are met. So in control systems, this is kind of how like your HVAC system knows, hey, I only should turn on the air conditioner part if my temperature goes above a certain point, and I should only turn the heater on if my temperature goes below a certain point. But also, I shouldn't short cycle my compressor by switching things on and off, like it has a dead band, like you guys talked about in the Engineering 120 series, so that you don't constantly turn things on and off. So again, doing something that you guys have done before with a microprocessor using analog signal processing. So the last case is going to be the negative feedback configuration. And that's going to look something like this. So when we had positive feedback, we had our our output signal fed back from the output to the non-inverting input. Well, in a negative feedback system, we're going to have that same feedback path, RF, but now it's converting our output terminal, or excuse me, connecting our output terminal to our inverting input terminal. We could put some resistor Ri here and then apply some input signal here. And this is a negative feedback configuration. So just to recap things really quickly here, open loop just means there isn't any feedback path whatsoever. So the output is not connected to either input terminal. In a positive feedback configuration, the output is connected through some conductive path. It might be a resistor, a capacitor, inductor, or a wire to the non-inverting input terminal. And then in a negative feedback configuration, our output is connected through, again, some conductive path, resistor, capacitor, inductor, or wire, directly to the inverting input terminal. And this negative feedback configuration is how the overwhelming majority of mathematical operations are carried out using op amps. Okay. So I mentioned this a few minutes ago, I think, but the only circuits that we're going to concern ourselves with here in Engineering 221 are going to be negative feedback circuits. And luckily for us, in a negative feedback configuration, uh, an operational amplifier is incredibly well behaved. Okay. So there's really just going to be two basic rules that we have to follow when analyzing negative feedback op-amp circuits. And if we can apply those rules correctly, this isn't particularly harder than any DC circuit analysis that we've done previous. So I want to talk about those two op-amp rules with you guys really quickly. So these are what are called the ideal op-amp rules. For what it's worth, they can be applied to almost 100% of negative feedback op-amp circuits because negative feedback makes the amplifier act very, very close to an ideal op-amp. If you want to get into the nitty-gritty of it, you can watch my videos where we talk about negative feedback in circuits too. But realistically, you should see that even for a poorly designed op-amp, when it has negative feedback in place, you will only have less than 1% error if you just assume it works as an ideal op-amp. So we're going to assume that all of our op-amps in this class are ideal. Okay. So there are two rules. The first of which is that no current can flow into or out of the input terminals I'm underlining input because that's the only thing that we have a constraint on. So of an ideal op-amp. So no current flows in or out of the inverting input terminal or the non-inverting input terminal. So the reason why this rule exists is because traditionally, operational amplifiers are biased using kilo-ohm size resistors. Okay. The internal input resistance of an op-amp is usually on the order of a mega-ohm if it's BJT based, or a tera-ohm if it's MOSFET based. So that's 10 to the 6 ohms for bipolar junction transistor technology, and 10 to the 12 ohms for metal oxide semiconductor technology. So if we use a kilo-ohm size resistor to bias this circuit to make our connections and things like that, it's roughly 1,000 to 1,000,000,000 times smaller than the internal resistance of the op-amp. So all of the current flows through the biasing resistor. Practically none of it flows into the op-amp itself, okay, or at least the input terminals of the op-amp. So that's where that rule comes from. Our second ideal op-amp rule is that there can be no potential difference between the input terminals, excuse me, of an ideal op-amp. So I'm going to write this in a note down here. I'm going to say that V plus, where this V with a subscript plus sign just means the voltage with respect to ground at the non-inverting input terminal must be equal to V superscript minus, where that V minus is the voltage with respect to ground at the inverting input terminal. Another way to think about this is V plus minus V minus will always be equal to 0 volts. So when we start analyzing a circuit here in a minute, we'll see how these rules are applied. Um, so what I'm going to do with you guys here is I'm actually going to wind up working several of your web work problems with you here. Okay. Homework number 16 is really all about understanding the rules, and these problems are pretty okay, so we're just going to kind of use them as our examples, and then we'll pivot away and start looking at a little bit harder things here towards the end of the class. Okay. So our first example, which is going to be similar to homework 16, problem 1, is going to look something like this. I've got my op amp over here, putting the inverting input terminal on top, non-inverting input terminal on bottom. I'm just going to label this voltage right here. So this is going to be V minus. This is our voltage at our inverting input terminal with respect to ground. Here is our non-inverting input terminal. I'm going to label this guy V plus. And then here is our output terminal, V out. So we have some resistor in our feedback path, and I'm just going to choose an arbitrary value. So let's say that this is 0.9 kiloohms. I'm going to ground my non-inverting input terminal, and I'm going to apply a current source to my inverting input terminal like so. And let's make this 3.1 milliamps. So our ultimate goal here is to determine what the output voltage is for this particular circuit, okay? And once we figure this out, I'm going to make a couple of additions to this circuit specifically so that we can see how they impact things, okay? So for this first example, I'm going to walk you guys through the process that I tend to employ whenever I'm looking at a negative feedback op amp circuit, okay? So step number 1 is going to be apply op amp rule number 1. So all I'm going to do on my diagram here is I'm just going to make a note that no current can flow into my input terminals. That is me applying op amp rule number 1. Okay. Step number 2, I'm going to find V plus. So this is just the voltage measured with respect to ground at my non-inverting input terminal. So I would like for one of you guys to look at this schematic diagram and take a stab at telling me what V plus should be for this circuit. Trevor said that the answer should be 0, and he is absolutely correct. If our non-inverting input terminal is connected directly to ground, then the voltage present at the non-inverting input terminal is indeed 0 volts. So I'm just going to make a little note here that this voltage, V plus, is equal to 0 volts. And now we're going to move on to step number 3. So our third step is going to be apply op amp rule number 2. So op amp rule number 2 told us that there can be no potential difference between the input terminals of an ideal op amp. So essentially what we're going to do is we're going to say that the voltage at this node, V minus, is also going to be 0 volts. Because if V plus is 0 volts, then V minus has to be 0 volts in order for op amp rule number 2 to be satisfied. Is everybody okay with that? Nobody's telling me they're not okay, so we'll move on from here. So step number 4 is going to be apply Kirchhoff's current law at the inverting input node. So essentially what I'm going to do is I'm going to add this current plus this current together and set them equal to 0. Okay. I don't need to worry about the current that's flowing to the right into the inverting input terminal because I know that that is 0. Okay. So what's my current flowing to the left through the 3.1 milliamp source?
Negative 3.1.
Negative 3.1 milliamps. Thank you. That is absolutely right. And now I'm going to figure out my current flowing to the right. So my voltage V minus and my voltage V out are both measured with respect to ground. So I'm going to treat this like I'm performing nodal analysis because essentially I am. So my current that's flowing up and to the right through that 0.9 kilo ohm resistor is starting at a node where my voltage is 0. So I'm going to have 0 volts minus, and that current is flowing to my output node. So I'll put V out. And now I'm just going to divide by the resistor value of 0.9 kilo ohms and set this equal to 0. So that's what my KCL equation looks like. Again, it's exactly as if I had written a nodal analysis equation at that particular node because all of the voltages that we're dealing with are measured with respect to ground. So they're all nodal voltages. Okay. Step number 5 is just going to be solve our equation for V out. So in this case, we would have, so I'm going to move that 3.1 milliamps over to the other side. So it's going to look like 3.1 milliamps is equal to negative V out over 0.9 kilo ohms. Well, I can get rid of this minus sign by putting a minus sign over here, and I can get rid of that 0.9 by multiplying both sides by 0.9 kilo ohms. And so throwing this into my calculator because I can't do that in my head very easily, 3.1 times 0.9 comes out to be negative 2.79 volts. So just to bring things back to what we talked about a little while ago, I applied a positive input signal and I got a negative output signal because my input was applied on the inverting input terminal side of the system. Okay. So before I start messing with this, does anybody have any questions or anything? Did this analysis process seem particularly difficult?
No.
Great, because it shouldn't be. This little 5-step process will work for the overwhelming majority of the op-amp circuits that you are going to deal with in this class, and it will also work for the overwhelming majority of the op-amp circuits that you might ever asked to be to physically, goodness gracious, you might ever be asked to implement in a real system. Okay. Um, I'll work a problem or two with the place where this process doesn't work because there's one or two of those in your homework. I will also rant about how utterly stupid they are, and it's pointless. But anyway, but if you can do this process, you can analyze practically any op-amp circuit. So now I want to mess with things a little bit before we move on to the next example. So what would have happened if I had added some resistance here between the output terminal and ground? I'm going to call this resistance R sub L because this is a load resistance. So our op amp might be driving some load like a small speaker. Okay. So would our analysis change at all if that RL were in the circuit?
No.
No, not even a little bit. Literally nothing would have changed. So for an ideal op amp, as long as our load resistance isn't zero, meaning that we are short circuiting the output node directly to ground and forcing V out to be zero, the value of RL is completely and utterly pointless from a circuit analysis perspective. Okay. Um, in a real system, the value of RL is actually important just because that's going to determine how much power is delivered to your load and all of that kind of good stuff. Okay. So from an analysis side of things, RL doesn't matter. From a practical implementation side of things, RL can be rather important. Okay. What if I had put a resistor here? So I'm going to call this guy R plus. Would that have impacted anything?
No, it shouldn't.
It shouldn't because there's no current flowing through that resistor. Because if current flowed through that resistor, there would be current flowing into the input terminal. So having a resistor connected directly to one of our input terminals like this will not have any impact whatsoever either. Again, from an analysis perspective, it does nothing but attempt to confuse you. From a practical perspective, it's going to try to negate what are called input offset currents, um, which are going to be incredibly small. So you would only ever do this for like very, very high precision amplification of a sensor or something like that. So most of us will never see this, but every now and then it is actually useful to physically put some resistor in series with the input terminal. But from an analysis perspective, again, it's not going to impact anything. All right, let's look at another example problem. So I'm going to take this same circuit and I'm going to make one change. Okay. It's a fairly impactful change for what it's worth. So this guy is homework set 16, problem 2. So I've got my op amp over here. I've got my negative feedback path connecting my output node to my inverting input node. Let's make this guy a 3.3 kilo ohm resistor. I'm going to have a current source over here again. So let's make this 4.1 milliamps. And now the thing that I'm going to change is instead of shorting out my non-inverting input terminal, I'm now going to apply a voltage source. So let's just make this guy something easy like 2 volts. So we're going to analyze this circuit twice, actually. Once using the 5-step method that I just showed you guys, because it's easy. But then we're going to look at it using superposition just so that we have a kind of basic understanding of what's going on. Okay. So my first step is to apply op amp rule number 1. So that's just me saying that this current is 0 amps and this current is 0 amps. My second step is to find the voltage V plus. So I'd love for one of you guys to tell me what the voltage is at this node with respect to ground. This isn't meant to be a trick question.
So it's just 0.
It is not 0. Trevor is correct. It is 2 volts because there is a 2-volt source connected between that node and ground. Our next step is to apply op amp rule number 2. So I would appreciate if one of you guys could tell me what voltage we'll see at this node. Also 2 volts. Thank you, Trevor. So it has to be also 2 volts because if V plus is 2 volts, then V minus has to be 2 volts in order for op amp rule number 2 to be satisfied. So whatever voltage we find at the non-inverting input automatically gets applied at the inverting input. Step number 4 is to apply KCL at the inverting input node. So that's going to be me adding this current plus this current together. And I would once again appreciate one of you guys' help in writing this equation. So what would the current flowing to the left through the current source be?
Negative 4.1 milliamps.
So negative 4.1 milliamps. And then how would I define the current flowing to the right using these effective nodal voltages?
That would be 2 minus V out over 3.3 kilo ohms.
So 2 volts minus V out over 3.3 kilo ohms. Oops, I put that on the wrong side of that 3. Let's set this equal to 0. And then step number 5 is just to solve, goodness, for V out. So I'm just going to use the numerical solver on my calculator here because I'm too lazy to do this much algebra. I believe we'll get negative 11.53 volts. Did anyone else get a similar result if they threw that expression into their calculator? All right, well, I'll just assume I'm right.
Yes,
So,
I did.
okay, thank you for that, Colin. Um, so circuit was, incrementally more difficult because there was that extra voltage source, but the five-step process worked just as well and all of that kind of stuff. I want to look at this from a superposition perspective, just really quickly, so that we have some kind of intuitive sense of what's going on when we apply an input signal on the non-inverting side versus when we apply an input signal on the inverting side of things. So you guys don't need to copy this down because I'm not ever expecting you to actually do superposition on these, although you can if you want to. I just want to kind of look at what's happening. So this is our original circuit. Let's look at it with VS on and CS off. Okay. So with our current source off, that is literally just going to be an open circuit over there. So we would have something akin to this. I'm not going to write down all of the steps again. We're just going to kind of do a quick and dirty analysis. So I know that this current is 0. I know that this current is 0. I know that this voltage is 2 volts, which means I know that this voltage is 2 volts. So let me ask you guys a slightly different question here. And this could be solved by applying KCL at this node if you wanted to, but I think we can do it intuitively. What's the voltage drop across this 3.3 kilo ohm resistor?
2 volts.
I disagree.
It's 0.
Joseph, you're right. Could you tell me why it's 0?
Um, uh, mm,
How much current is flowing through that 3.3
0
kilo
amps,
ohm
so
resistor?
volts over 3.3. 0 is equal to that.
Yeah. So since no current can flow into or out of the input terminals, and the 3.3 kilo ohm resistor is connected directly in series with one of those input terminals, we know that there's no voltage drop over it. So what does that tell us about our output voltage? Well, if we were to do Kirchhoff's voltage law around this system, so we could do something akin to this. So if we started here at ground, and actually I'm just going to make a little note right here, explicitly showing that V out is the voltage measured at the output terminal with respect to ground. So if I started down here, I would have negative 2 volts. Then I go across my input terminals. Well, I know there's no potential difference between my input terminals, so that looks like 0. Then I go across my 3.3 kilo ohm resistor. That looks like 0. And then down this path back to ground. Essentially, what I wind up getting is that negative 2 volts plus V out is equal to 0, let me call this V out prime, which means V out prime is just 2 volts. So I applied a positive input signal to the non-inverting input terminal, and I got a positive output signal. Because I only have a feedback path and no other conductive path connecting my inverting input node to ground, all of my signal from my input reaches my output. Now, when we look at this circuit with VS off and CS on, we have this guy. I didn't bother writing the values here, but this is literally just the first example that we worked. And we found out that our output voltage was simply negative our current times our resistor. So if you do negative 4.1 milliamps times 3.3 kiloohms, and then you add 2 volts to that, which is the contribution of the voltage source, you will get this result, okay? So it's just a different way of looking at things. I just wanted to show you guys that, again, if you apply a positive input signal to the non-inverting input terminal, you should expect to get a positive output signal. If you apply a positive input signal to the inverting input terminal, you should expect to get a negative output signal. If you apply signals to both, you're going to get a combination of the two. Okay, so. All right, before we move on to our next example problem, does anybody have any questions? Okay, so we're going to take a break from solving homework problems here, and I'm going to give you guys something that looks utterly terrifying, okay? So like this is the type of circuit that I like to put on your exam when I'm in a really bad mood when I'm making out the test. And I want to show you guys that even though it looks wildly complicated and way more difficult than either of the 2 examples that we've worked, we can legit just use this basic 5-step process in order to solve it. So there's really no way I can make op-amp circuits hard because they're just inherently not that difficult. All right. So starting with my op-amp, so let's do something gross like this. Let's say that this is a 1.6 kilo ohm resistor. Let's put a 3.1 kilo ohm resistor here. And let's make this extra difficult and put a voltage source here. Let's just make this a 2-volt source again. This is the non-inverting input side. On the inverting input side, starting with my feedback path, let's put a 4.5 kilo ohm resistor. Let's make this a 1 milliamp source pointed out. And then up here, let's make this a 4-volt source in series with a 2 kilo ohm resistor. And just for the hell of it, even though I've already told you guys that this actually doesn't impact anything, I'm going to put an 8.3 kilo ohm resistor between the output and ground. So this is, at least from appearances, a significant increase in the difficulty level of the circuits that we've been analyzing that contain op amps. But we can just use that same basic 5-step process and we won't really have any problems here. So, step 1 is to apply op amp rule number 1. So I'm observing that no current can flow into my input terminals like so. Step number 2 is to find V plus, which I'm just going to draw an arrow here. So we are finding the voltage at this node. That is going to be the same thing, for what it's worth, as the voltage drop across the 1.6 kilo ohm resistor, because our voltage V plus is the voltage at the non-inverting input node with respect to ground, and there is a 1.6 kilo ohm resistor connected between the non-inverting input node and ground. So all I'm interested in here really is the voltage drop across the 1.6 kilo ohm resistor. Before I tell you guys how to do it, I would love it if one of you attempted to figure out what it is. Or at least thought out loud about how you might do it.
Could we find the current that's flowing through the 2 volts in the resistors, because all the current's going through there and not the positive? So we find the equivalent resistance and then do 2 volts divided by the equivalent resistance to find the current and then multiply it by 1.6 kilo ohms.
So what West is suggesting actually is perfectly fine. And I will tell you a very slightly easier way to do it, but what you have suggested is 100% correct, or 100% true, okay? So what he said, so let me define this current here. So West figured out by just looking at this thing that any current that's flowing through this 2-volt source is going to flow through this 3.1 kilo ohm resistor, and then it has to flow down through the 1.6 kilo ohm resistor before returning to ground. So this is the path that the current is going to take. So if we say that our current I is just 2 volts divided by 3.1 kilo ohms plus 1.6 kilo ohms, and I'll figure out what that is in a second, then we can say that V plus is just I times 1.6 kilo ohms. So let me throw that into the calculator really quickly. So 2 divided by 3,100 plus 1,600 winds up giving me 0.426 milliamps. And then if I multiply that by 1,600, I wind up getting 0.681 volts. So, fantastic job, West. Nothing remotely wrong with your thought process there. I just want to mention an easier way to do it. So, and again, this is based off of West's observation. So if there's no current that is allowed to flow to the right through into the input terminal, then, and Jaime just nailed it, we can just treat these resistors as if they are in series and use voltage division. Okay, so Jaime is absolutely correct. So the second way to do this would be V plus is equal to 2 volts times 1.6 kiloohms over 3.1 kiloohms plus 1.6 kiloohms, because we're interested in the voltage between the inverting input terminal, excuse me, the non-inverting input terminal and ground, which is the voltage drop over the 1.6 kilo ohm resistor. So we would have 2 times 1.6 over 3.1 plus 1.6 comes out to be 0.681 volts. So either way works. For what it's worth, and this would be utter overkill for something like this, but you could technically do it. You could, if you were so inclined, disconnect everything to the left of that dashed pink line and find its Thevenin equivalent, which would actually give you that voltage of 0.681 volts as well. Finding the Thevenin equivalent and then reattaching that Thevenin equivalent will make it look more like the examples that we've worked previously. So not expecting everybody to do that, but if you were ever in doubt, you could actually use the Thevenin equivalent circuit to simplify portions of these networks to make it look like things that you've seen before. Okay, so we have figured out V plus in a couple of different ways. So now let's do op amp rule, excuse me, step number 3, which is to apply op amp rule number 2. So that's just telling us that this voltage right here is also 0.681 volts. I was just storing that in my calculator. Step number 4 is to apply KCL at the non-inverting input node. No, that's wrong. At the inverting input node, my apologies. So that will be adding this current plus this current plus this current together. So could somebody tell me what that equation would look like?
Would it be 4 divided by 2000? It should be negative as well. Negative 4 over 2000.
So
1
let me
millivolt?
stop you there, Colin. So that negative 4 over 2000 would only be true if V minus were 0 volts, but we just proved that it isn't. So how would you take into account that V minus isn't 0?
Is it not just 0.68 minus V out over 4.5?
So there is going to be a 0.681 volts minus V out over 4.5 kiloohms. That is the current that's flowing to the right. What about the current that's flowing to the left through the 2 kilo ohm resistor?
Shouldn't that be 0.681 minus 4 over 2000 ohms?
So 0.681 volts minus 4 volts over 2 kilo ohms. Okay. And then what about the current flowing to the left through the current source?
is just 1 milliamp.
So plus 1 milliamp is equal to 0. Okay. And then step 5 is throw this gross thing into our equation solver and solve for B out. So I'm going to try to do just that. I'm using one of my Casios, so hopefully this doesn't go too far askew for me. So I got V out is equal to negative 2.287 and some change volts when I threw that into my Casio equation solver. I think Trevor's giving me a thumbs up that says that's correct. West got that as well, so I will assume that the three of us are correct. Okay. So that is literally damn near the hardest thing I could possibly throw at you. It's got multiple input signals on both the non-inverting and the inverting side of the amplifier. It's got extra resistors thrown in there to try to confuse you, all of that kind of stuff. And our simple 5-step process worked. Okay. So the last example that I want to work with you guys for today is one of the very rare instances where our 5-step process won't work. And technically speaking, we could adapt it and make it work by using the concept of supernodes, but that's kind of overkill for this. Okay. So this will be example number 4, if I remember correctly. And this guy looks a lot like homework 16, problem 3. So starting with our op amp. Flip those guys around. So here is my feedback path. And let's see, let's make this guy over here 4.8 volts, this guy 3.9 volts, and this guy 1.8 kiloohms. So essentially, if we have a voltage source in our feedback path, then it makes it harder to apply KCL at our inverting input node. Okay. So we're going to have to do something else. Now, that being said, there is literally no practical reason why you would ever actually include a voltage source in your feedback path. So this isn't something that you will ever experience in real life. This is just the person who made the WebWork problems being a jerk. Okay. So I'm going to work this problem with you. I think there might be one more similar to this in this homework set. And then other than that, you will never see this type of problem again. So what we're going to do is something really similar. Okay. So first step is going to be apply op amp rule number 1. So here is our current. 0 amps flowing into both of our input nodes. Then we are going to find V plus. So can somebody tell me what the voltage is at this node? 4.8 volts. Thank you, Trevor. So what's the voltage at this node? Sorry, let me write down step 3 while somebody answers that. Trevor is also correct again. This one is also 4.8 volts. So as I mentioned a moment ago, we could, if we were so inclined, treat this thing as a supernode and keep our 5-step process alive. But I actually think that this is overkill, so we're not going to do that. So I'm going to do step 4 with a star in a different color. And instead of doing KCL, we're going to do KVL. Um, so I'm going to start at ground and end at ground, much like I did up here. Okay, so same basic thing. I'm going to make a note here, just so that it's super obvious once again, that the voltage present at our output node is measured with respect to ground. So my KVL equation starts here, goes up here, across, and then down like so. So that would look like negative 4.8 volts. Then there's no voltage drop across my input terminals, according to op amp rule number 2. So now I would see the positive polarity terminal of my 3.9 volt source. So now things are getting a little interesting. What should the voltage drop across my 1.8 kilo ohm resistor be?
3.9 minus V out.
I disagree. How much current is flowing through that 1.8 kilo ohm resistor?
0.
0. Because any current flowing through that 1.8 kilo ohm resistor would be flowing into or out of the inverting input terminal, right? So op amp rule number 1 is superseding our baser instincts of using Ohm's law to find that current. So no voltage drop across the 1.8 kilo ohm resistor, which means we just have plus V out is equal to 0. And now we're back to step 5. Solve for V out, which in this case, that's going to be 4.8 volts minus 3.9 volts is 0.9 volts. So like I said, having the voltage source in the feedback path doesn't make this circuit that much harder. We just have to either change step 4 to use a KCL out of a supernode or KVL around the circuit, and then we'll wind up getting the result. I want to say homework 16 problem 5 is very similar. Yeah, it's almost the exact same circuit. It's just drawn differently and there's no resistor there. So those are the only two examples that you should ever see where you have a voltage source in your feedback path. All right, I have ranted about op amps and work circuits with you guys for a good hour and 20 minutes. So you're free to work on your in-class assignment if you so choose. If you have any questions or anything, I would be more than happy to answer them. And if not, I'll see you on Friday.
Dr. Harmon, I have a question about number 6. I'm sorry, you can answer Trevor's question first.
Trevor, I have not goodness gracious. I have not posted it yet. I'm still working on it. I just want to make sure that all of the correct answers are actually available. Yeah. So your focus right now should probably be on exam 2 related stuff. I'll make sure that you have plenty of time to do the bonus op. So yeah. All right, Colin, what's up?
We looked at number 6 on homework 16.
Homework 16, problem 6.
Yes, sir.
Okay. What about it?
With that problem, the current that would be flowing from the negative terminal, would that current be split into R2 and then the rest would be into R3? Is that correct?
So let me pull this over so that I can use my mouse to describe what's going on, right?
Yes, sir.
So you can see my mouse and all that kind of stuff, right?
Yes, sir.
Okay. So when you apply KCL at this node, there's going to be some current flowing to the left through R1.
Mhm.
There might be some current flowing down through R2. We'll revisit that in just a second. And there's going to
Okay.
be some current flowing up and to the right through R3. So you would have 3 terms in your KCL expression. Okay.
Yes, sir.
Now let's revisit this R2 thing. What is the voltage present at the non-inverting input node, which would be this node right here?
It'd be 0 volts.
Okay, so that means what's the voltage at this node?
0 volts.
So what's the total voltage drop across R2?
0.
0 volts. So there won't be any current flowing down through this one. So in your KCL equation, if you included it, it would just be 0 minus 0 over R2, which is obviously 0.
Okay. That makes a lot more sense. So then your current would just be VS divided by R1 and R3 in series.
You would have, so the current flowing this way would be 0 minus Vs over R1. The current flowing this way would be 0 minus V out over R3, and then solve for R out.
Okay.
Excuse me, V out.
All right. Thank you, sir.
Yep.